The purpose of this lesson is to represent Peano arithmetic terms, formulae, proofs as natural numbers by a primitive recursive coding function, to speak of the theory inside the theory, up to the coding. To simplify our treatment, we assume all the variables to be xi, with I a natural number. The coding function g is defined as in the slide. Since we use just multiplication and exponentiation, g is primitive recursive. By the prime factorization theorem, g is injective. On the image of g, its inverse is primitive recursive, since division and logarithm are so. The coding function, by its structure, allows to tell when a number is in the image what kind of term it codes and what specific instance of a term. Hence, we can decide whether a number represents a term and eventually extract the codes of its components. And by proposition 71.7, all these actions can be done by formulae in Peano arithmetic. The coding function g is easily extended to formulae as in the slide. The same remarks on g apply. Again, the coding allows to dismount the formula, and the codes of formulae form a recursive set disjoint from the one of terms. As before, thanks to theorem 71.7, we can represent the set of codes for formulae and the dismount function by appropriate formulae. Before coding proofs, we need a way to code finite sequences of natural numbers. This is simply done as in the slide. Again, the coding function is injective primitive recursive with a primitive recursive inverse, and the set of codes for sequences is disjoint from the other sets of codes. It is recursive, thus representable, and the dismounting functions are representable too. Finally, we extend the coding function g to proofs in a similar way. Actually, we slightly relaxed the notation, allowing to code sequences of elements rather than sequences of naturals only. As one should expect, the previous characters of the coding function are still present. It is injective primitive recursive with a primitive recursive inverse. The set of codes for proofs is disjoint from the other codes, and it is recursive. And finally, it is easy and computable to take pieces apart. The numerals of terms, formulae, sequences, and proofs are nothing but the value of g written in the syntax of Peano arithmetic. By numerals, we can write properties of terms, formulae, proofs as properties of their codes inside the language of the formal system.